So, hello, my name is Simpiwe, and I'm an earth scientist by training and a science communicator by experience. So, I basically want to just simply talk about science concepts, and acknowledge that in as much as study of the science and contribution to the sciences by people that have studied to their masters and their PhDs and are doing experiments and research, that might be with some level of complexity and depth. But people need to understand that science is all around us. Science is everything that is around us, and it's all interlinked, interconnected. In grade school, you might have subjects. In university, you might talk of modules and courses. But the fact of the matter is, science can be expressed with context of everyday life, and it can be explained using demonstrations and analogies so that people are more science literate. They are more open to the sciences and understand the importance of it, and they can relate better with it. So I'll try to, very simply, I'm a simple guy, I'll take it back to the basics first and foremost, take it old school. I gesture quite a lot, but I'll also use the chalkboard behind me. But for now, try to concentrate on what I'm saying, and obviously I'll now direct you whenever I want your attention on the board as well. So we'll talk about the Earth and beyond. So from planet Earth, talking about it, and then looking outward into the universe. Let's start from the ground up. Now we know we are on planet Earth, which is a rocky planet. You have the land masses, which are the continents, and the oceans, which take up the bulk of our planet. Also, you'll find that the planet itself is roundish, it's spherical, but it's not a perfect sphere. You have areas of varying height above sea level, mountain ranges, low-lying areas. But broadly speaking, talking about the globe itself, it might look perfectly round, say from pictures from out of space, in outer space, pardon me, out of the planet. But it is an oblate sphere, which simply means it is flattish at the poles and a bit heavy around the midsections. It's basically bulging around the equator area. So it's mid-heavy, this planet of ours. But basically, I want to begin by explaining processes and how certain things follow and how they link to the lives that we live. Let us now say we are on a mountain. We are looking at a mountain. So it's a place of higher altitude. You might have big boulders there. Over time, these boulders are exposed to the elements. There's rain, there's snow, there's sleet, and a host of other things. And on cold days, they contract. On hot days, they expand. And over time, cracks might form, and water might get into those cracks, cause a bit of working on that rock. Water might freeze when it is cold, gaining a bit of volume, forces the cracks to be a bit wider. But over time, geological time, talking of longish time scales, through geological time, those boulders might get weathered, and you'll find that they can become rocks, smaller rocks and stones. And as time goes on, they might even become soil, which, if it's right on the edge of a mountain range, for example, on a cliff, you might have debris fall because gravity pulls things down, right? Or you might have that material being moved downslope by water after it has rained. It's transported, this material, or it can be through wind erosion, but it's transported downward from a place of high altitude to a place of low altitude. That material might be deposited then. Weathering occurred, material was eroded, transported, deposited. Now, material that might be deposited in this area of depression, which we call the sedimentary basin, is this material. It's formed of the rocks, the stones, soil, and organic material. dead plants, it could be organisms that may have also lived along that stretch and died off. And all of this we call sediments. New material might come and cover the older material, and that material gets buried a bit deeper into the ground. It might aggregate, come together to form rocks. Those rocks we will call sedimentary rocks because they were built up of sediments. New material will still come to the top while older material gets buried even deeper. That material will be exposed to different temperature and pressure conditions, and there might be changes, physical and chemical. And we call them metamorphic rocks because they've gone through a process of metamorphosis. They have metamorphosed. So it's a process of metamorphism. Alright? So it's metamorphic rocks in the end. That material can get buried even deeper into the ground, and as you go deeper into the ground, it becomes hotter. That is why even mines, when they need to dig deeper, they know they have to work on air circulation and cooling system for the mine workers and whatever machinery that might need to cool down. Basically, this material gets to a point now where it is so hot that it starts to melt and it becomes molten material. This molten material is much the same as you'd have custard or porridge in a pot that is boiling, and it's under so much pressure, and it's looking for an avenue, looking for an area of weakness through which it can escape. And similarly, the custard and the porridge example, it's in a boiling pot, pushes the lid. If you are not watching it carefully, pushes the lid and it spews out on the side. That molten material, which we call magma, when it's still in the subsurface underground, finds these areas where the ground has openings. It widens those openings, moves upward. It might form a hill or a mountain, basically pushes against the surface of the earth. And in other instances, depending on energy levels and the material, it might cause volcanoes. Then you have eruptions, material coming out of the surface, highly energetic. You might have rocks flying out in different directions. You might have all this material, this slurry of molten material. Once it gets to the surface, we call it lava, L-A-V-A, lava. Over time, this material might cool, forming certain types of rock and minerals, and you will have had recrystallization and coming together of these elements and minerals, and we call them igneous rocks because they've gone through a process of ignition. They've been ignited. They've gone through a fire situation, fire circumstances where they were burnt up, they melted, and they changed in how they are, and now they are coming back to the surface as new material, basically. So you have a recycling of material. But now you understand that you have this mountain range that it is formed, or a volcano which has spewed out all this material, which in time will get weathered again, and that material will go further downslope to become sediment, and the whole process essentially over a long time period will repeat itself, and that we call the rock cycle. I hope it makes sense. Now we look at it from a different perspective. Still the same material being moved from a place of higher altitude further downslope. So rocks have now become stones, have become soil, material is moved down, wind erosion, water erosion, and what have you. You'll have the different soil types. You'll have your loam soil, your silt, your clay, you'll have your sand. But basically, the more fertile soil will be conducive for plant growth. And then you find that further downslope, you have vegetation growing. This is just now introducing a different science, right? But surely you can now see the link as it begins. Now you have vegetation growing from that soil. This vegetation grows because it gets the nutrients from the ground through its roots. It gets water. It is able to draw carbon dioxide from the atmosphere. It is able to draw energy from the sun. And it goes through this process of photosynthesis. And as a byproduct, it gives off energy into the atmosphere. You might also then have organisms that feed on those plants, and those organisms are called herbivores. Those organisms might also have things called predators that prey on them, and those predators feeding on these organisms that feed on the plants will be carnivores. So carnivores are feeding on herbivores, herbivores are feeding on the plants. And then you have us, human beings and baboons and pigs even. And we feed on other organisms, on other animals specifically, and we feed on the plants as well. So we are omnivores. Through this, you have also what's called energy transfer. Energy from the sun was taken by the plants. The plants have now transferred the energy to herbivores. Herbivores transferred it to carnivores and or the omnivores. So we are getting this energy directly from the plants, or we can get it from animals that have received it from the plants. Very interesting as well with plants is they take away carbon dioxide from the atmosphere. They give off oxygen. What do we need to breathe? What do we need to be alive? Oxygen. What do we breathe out? Carbon dioxide. So you have this process of exchange with the plants. We receive oxygen from the plants. We give them the carbon dioxide that they need for their process of making food, which is photosynthesis. Where they're getting the energy from the sun, getting carbon dioxide from the atmosphere, and of course other nutrients from the ground and all of that. Then in that process, we are finding this interlink as well, and the ecological cycle to a very simplified extent. Now another cycle is the water cycle or hydrological cycle, where we can begin with the plants. We said the plants have roots which are in the ground. They draw water from the ground. They get nutrients. They basically use the water, and some of that water might get to their leaves and other parts, and some of it might get lost to the atmosphere, and we call this transpiration. A bigger scale example of this, which is evaporation broadly, is that you'll have water bodies. You'll have rivers and dams and lakes on the continents, and then you'll have the oceans. When it gets really hot, that water heats up. Certain molecules will come off that water body as vapor. They move through the atmosphere, but they get to a point high up where temperature has changed, conditions are different, it condenses. You'll see formation of clouds. Those clouds will form to a certain extent and then start giving off precipitation. That material will have gone up from the water bodies, became less dense because it's now heated, moves up through the atmosphere, gets to a point where it condenses, forms clouds, and then precipitation happens. It can be hail, it can be sleet, it can be snow, it can be rain as in water, but basically you have this cycle of water. So you might have it as evaporation broadly, or transpiration in the specific case of vegetation, where water is moved from the ground, moved through the plant as it uses it. Some of it gets lost through its leaves, and it evaporates from there into the atmosphere. Now let us move forward, perhaps adding just a layer to that hydrological cycle, where water is now coming down, precipitation gets to the ground, and this precipitation, depending on how heavy it might be, will form, if it's rain, sheet flow, where it's this layer of it just going on top of the ground, downslope, following the gradient due to gravity dynamics. Or you might have it if it's a slight drizzle, or it's not heavy rain, it hits the ground, it percolates, it moves through the soil, and as it moves through the soil, it will move through different types of rock and it will interact with that, and it gets finally to a water table, that level of water deep underground, which fluctuates depending on how much it is recharged, that whole system, or how much it is discharged, either that water being lost to dams or the ocean, or even extraction by us, boreholes and fountains and all these other things. Alright, I think I've made the point with that one. Hydrological cycle, ecological cycle, and the gaseous cycle, just touching on carbon dioxide and oxygen there, and also the rock cycle. Now let's look at planet Earth and its layers, and then we'll move upward and outward. So planet Earth is this roundish planet, rocky planet. It's the sphere, oblate sphere, which is flattish at the poles and bulging a bit around the equator. It has layers. It has the topmost layer, which is called the crust, which on average is about 30 kilometers in thickness. Other texts will say even goes up to 50 kilometers. It's different in terms of thickness between what it is on the continents and on the ocean floor. So it's very thin on the ocean floor, very thick on the continents where humans live. Now, below the crust, you'll then have the mantle. Below the mantle, you'll have the core, which is the outer core, which is molten material, and then you'll have the inner core, which is a solid iron alloy, mixture of metals that are so pressurized that it has become solid and is compact. And the inner core, you'll get it depths into the ground of around 6,300 kilometers or just a bit more. Now, we live on the crust. The mining that we do, we are extracting from the crust. And being on the crust, there are processes that take place. There are processes that take place. Our planet is not static, it is dynamic, it is moving, it is alive. It's not just us that are alive. Basically, we mean that the planet changes. There are processes that take place, a whole lot of things that change how it is over time. Now, we said the planet is roundish. So, on the planet, we have things called tectonic plates. Tectonic plates and areas of activity where these plates interact. You might have interaction in this direction, we'll talk of shearing. Then you might have areas, broadly speaking, where we say there's convergence, meaning they may have been some distance apart, but they are coming together, they're converging. Depending on the density of the plates, where they might link up to continents, when they interact, there might be a collision that leads to accretion, coming together of material. And as this material comes together, because these blades are of similar density, they float to the same extent on the layers of the earth that are below. They come together and they form a mountain range, much like you'd have the Himalayas around the India continent, where material is moved together and mountain ranges may have formed. In other instances, you might find that there's a convergence, so but you have one being less dense and another being more dense, such that this one which is less dense is more buoyant. It overrides this other one, and this one will sink deeper, and we call that a subduction zone. And as that happens, there is friction. There might be seismic activity. A lot of volcanoes or earth tremors and earthquakes might happen in places like these. And you have this material going deeper into the earth, and it breaks off a certain piece, and it gets recycled. So you have a recycling of material by planet Earth. A lot of the landmass that we live on is recycled, of course, over geological time. And as it is getting recycled, you'll find that some minerals are being trapped inside the planet, and some material is now being released. And I'm talking in terms of gases and minerals and all this type of things. And that is very important because it talks to what we have in the atmosphere available for us to live. And you have all these different compounds and other things that are able to form. It's because you have this availability of material and the recycling of it. Now, getting back to the dynamics of the Earth, we talked of a convergence zone where material and the plate tectonics are such that the plates come together, they collide, they form mountain ranges. It's upward movement like that. And in other cases, you have subduction. Now, because the planet is round, you'll find that some places have plates, tectonic plates that are moving apart. And where you have others moving apart, at another place you'll have others moving closer together. And when they move apart, they are opening a gap. And where that gap is usually opened, it's where the molten material may come up from the surface to fill up that space. And in effect, it drives some of that movement because this material wants to get to the surface. Therefore, if there was a crack, it forces it wider, opening up space for more material to get to the surface. And still going back to that recycling of the material. So you find that the Earth is very dynamic, and you find that we are moving, though very slowly, and that is why we do not feel it. We are moving very slowly. You have continents moving closer to one another and others moving farther away from one another. And we might broadly call it continental drift. All right. And I think just touching on the layers of the solid Earth, we are done. We can move to layers of the atmosphere. That's the air we breathe, where we have a carbon dioxide, your nitrogen, oxygen, and all these other ones. But the most important one to us, of course, is that it's oxygen needed. We breathe oxygen in. So you have this atmosphere, this layer of atmosphere. And if you move through the atmosphere, as we do when we launch rockets or people into outer space, they move through the atmosphere. Once you get to the exosphere, and I say exosphere, that word exo, it talks to something being the outermost or outside. You talk of organisms that have an exoskeleton. It means it has a skeleton outside of the body, unlike us, which we have inside. You'll talk of, for example, exoplanets, and those are planets that exist outside of our star system, which is the solar system. We have lots and lots of other stars, and they also have planets going around them, and we call them exoplanets. But coming back to us moving from the ground up, we move through the atmosphere, we get to about 100 kilometers above the ground and beyond, and we say we are in outer space. Once we're in outer space, let us say we are going to the International Space Station. We get to the International Space Station, we look back down, and we see our spherical planet, this blue planet, so full of water. Now I want to touch on things called satellites, because I said we are going to do this in the way of moving from the ground up and looking outward. Now we are outside planet Earth, and let us say this is planet Earth. And I'll define a satellite first. A satellite is an object that orbits another object. So you'll find that the moon is a natural object to planet Earth, and of course the other moons to the other planets. Planet Earth and the other planets are natural satellites of the sun because they orbit the sun. And planet Earth happens to take 365 days and a quarter to do so. But as convention would have it, we do not register that quarter up until we get to the 4th year, where we take that quarter, which is 6 hours out of a 24-hour day. On that 4th year, like it is this year, we add those quarters to form a day. We decide which is the shortest month. It's February. let's give it one more day, sham. Then it has 29 days. Then we have a leap year, February is a leap month, and the 29th of February is a leap day. But essentially, planet Earth takes 365 days and a quarter to go around the sun. Coming back to satellites, apart from the natural satellites, we also have man-made or artificial satellites, which are the ones that we have built on planet Earth and sent up with shuttles so that we are able to predict the weather, we are able to have global positioning systems, and a whole lot of other uses that we use them for. Now, very important, with satellites, they have certain orbits at which they move. Think of a racetrack, professional racetrack. Athletes will be running 100 meters, 200 meters, 400 meters. They have to stay in their own lanes as they run around. That is the same with satellites that orbit. They have certain lanes in which they are moving. And the closer a satellite is to that body it is going around, the closer it is, the faster it is going around that body. The more distance away from that center body, the slower it moves. Now I'll give examples here. You have what are called low Earth orbit satellites, which operate here. And they operate just beyond 100 kilometers above the ground to say around 2,000. Somewhere there. And they are very fast. They can take around even 90 minutes just to go around the planet Earth. Now, at higher altitudes, let me put it this way, higher distance away from planet Earth, you have the medium Earth orbit satellites. And those ones will be from around 2,000 kilometers above the ground to the 30,000s. And those ones are moving a bit slower, obviously, than the low Earth orbit satellites. Then you get to these ones, which are the high Earth orbit satellites. Pardon me. These are the geosynchronous Earth orbit satellites, right? So they are the geo, so it's GEO, all right? Geosynchronous means they are at a distance of 36,000 kilometers above the ground, and they move at the same speed as planet Earth does. And those are the ones you'd have for satellite television. In our context in South Africa, you'll find that if people have a particular brand, say DSTV, that they are using, all the dishes of all homes will point in a certain direction. And you will notice this if you're in a block of flats, because the satellite is always in the same position relative to planet Earth. They are always facing one another as they go around, as you have an orbit of the satellite orbiting planet Earth, and as you might have planet Earth spinning on its axis over a 24-hour period, giving us the night and the day, right? So low Earth orbit satellites, medium Earth orbit satellites, geosynchronous Earth orbiting satellites, all right? And then you have a special case of satellites, which, all right, and that is the one which is actually HEO, highly elliptical orbit. Elliptical means it's not rounded like you saw there. It's a bit of a curved shape like that. All right, so that is elliptical. Basically, you'll find that at certain places it's closer to planet Earth, and at certain places it's further away from planet Earth. But the important thing is that these other ones, LEO, MEO, GEO, are usually moving around the equator of our planet, and HEO cover much of the poles as well. and that is very important. And then, done with the man-made satellites or artificial satellites, we move to a natural satellite. I've drawn it very small, but it's basically the moon. I'll expand it just now. So that is the moon, a natural satellite to planet Earth, and the moon is 385,000 kilometers away from our planet, from the ground. And what's very important about this, it goes back to what I was saying about the farther away an object is from that center body, the slower it moves. And because the moon is that far away from our planet, it takes 28 days, roughly 28 days to go around planet Earth. Alright? So you kind of get the concept now. Moving right along, in the interest of time. So with this video, I just wanted to touch on all these different things. Person might watch this once or twice, but I'm hoping that through this, in a very simple way, a person can see how one of the sciences and or subjects or concepts might lead to the other, and they then understand that science shouldn't be intimidating. It shouldn't be something that's felt it's for certain people. All of us need to have a basic understanding of science, and I feel it's just a matter of how it's communicated to people and how it's made to be relevant for them in their everyday lives. Now let's continue. I'll just get this off the board very quickly, and then I'll continue. Old school indeed. Now we said our home planet is planet Earth, and we orbit the sun, which is a star. It's not the biggest, it's not the brightest, it's not the hottest. It just so happens that it's the closest one to our planet. So you have the sun, and you have how many planets again? 8 planets. It used to be 9, but in 2006 Pluto was demoted, became a dwarf planet. It joined the ranks of other dwarf planets that had been in existence. But the debate continued, and we've recently had pictures and flybys on Pluto, and people are still debating as to shall it remain a dwarf planet, or do we bring it back to the class of planets. But basically you have the sun, and then you have all these bodies going around the sun, orbiting it, and we happen to be the 3rd planet from the sun, and we have this advantage of being in the Goldilocks zone, like the sweet spot, where it's just the right distance away from the sun, and we have this atmosphere which protects us from a whole lot of things that come toward the planet. I mean UV rays, for example. The atmosphere assists us with that, and that it blocks it for us. But due to some activities that we are doing, we are eroding it, we are harming the ozone layer, and hence people talk of be careful of not getting a tan, basking in the sun between 12 p.m. and 3 p.m. Make sure when you're out in the sun, you're wearing a hat, you're wearing UV protective glasses, you're putting sunblock and all these things. But basically we also have a magnetic field. Our planet is a magnet, and we have a magnetic field, and that deflects the even more dangerous type of radiation coming toward our planet. But some of that is directed toward the poles. Talking about that radiation, some elements of it are directed toward the poles, and that's how you have these northern lights. People talk of aurora or aurora borealis, and people in certain areas of the planet are able to see these spectacular night sky lights. But basically we are protected as planet Earth because we have an atmosphere and we have a magnetic field. A planet like Mercury has a very negligible, very thin atmosphere. So in the day it gets very hot, but at night majority of that heat is lost. So Mercury can then not be the hottest planet in the atmosphere, in the solar system. Pardon me. Then you have Venus following Mercury, and Venus happens to be the hottest planet in our solar system because it has this thick atmosphere full of greenhouse gases, the gases that trap heat and don't let it escape. It has an acidic atmosphere. Temperatures can get to around 400 degrees And that's why we call it the morning star or the evening star. Sometimes we have this use of terms called Venus, the morning star or the evening star, and yet it's just a planet which has so much energy that it radiates its soul. And we now, depending on whether it came out before the sun in the morning, or it has come up after the sun is set, it can be evening star or morning star, in terms of the terms that we use to describe it. And then we have planet Earth, of course. I'll just leave it with those three, and then Mars, of course, which we are now trying to explore to see if there are signs of life, and people are even as ambitious to want to go and start a colony there, and perhaps have it as an alternative home for us. But basically, you have the sun, which is solar system, solar energy, and then you have the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? Not counting the dwarf planets. Okay. Now let's talk about the sun, and let's talk about other stars as well. I said it's not the biggest, it's not the brightest, it's not the hottest. It happens to be the closest one to our planet. Think of it this way. When you look up in the night sky and you see those dots of light, you know nothing about the distance or how big they are, except there should be an understanding that those are giving off light, and the fact that you are able to see them with the naked eye tells you that they might be very big and may have or have had so much energy that that radiation of theirs has even been able to reach planet Earth. So in a nutshell, you have stars that are bigger, brighter, more massive than our own, but they are very far away. And when we talk of telescopes being used to study all these objects, even the name itself tells us of the distance. You break up tele, that talks to the distance, and scope talks to that region or area of interest that you are looking at. Telescope. In Xhosa, for example, the television, we call it umabonakude. Literally something that shows me things far away from where I am. Just in the interest of talking of apparatus and instruments, equipment, sometimes people have said we use microscopes to study the universe. And the distinction is that telescopes talks of the distance, and you are looking at these objects that are massive, but because of the distance you need to magnify them to see them better. Microscope is looking at things that are very small, micro, they're very close to you, but because they're small, you need to magnify them as well to see them properly. Alright, so let me just wrap up by talking about the radiation types given off by objects such as stars. You might have heard of the electromagnetic spectrum, where it's radiation types of light, if you will, which are given off in all directions by these spherical bodies, right? We are designed to detect optical, visible, or white light, but the other ones we need different instruments that will detect them so that we are able to study them. Then people might ask, but why bother putting money into these things and allowing scientists to indulge in hobbies? But it's very important, because once we understand those, we are able to then use the same principles to our benefit. I'll give an example. In terms of the electromagnetic spectrum, starting from high energy to low energy, you might have gamma rays, you have X-rays, you have ultraviolet light, you have optical white light, you have infrared, you have microwaves, and then least energetic are radio waves. Gamma rays, X-rays, UV are not meant to penetrate our atmosphere and the magnetic field I spoke of earlier. Gamma rays we are protected from, X-rays we are protected from, UV, like I said, because we are depleting the ozone layer, some of it is getting through. But also, you find that optical does get through. That's how we are able to see one another and even see the spectrum of visible light, the 7 colors, where we talk of the colors of the rainbow, your red, orange, yellow, green, blue, indigo, violet, raw G beef, red, orange, yellow, green, blue, indigo, violet, and that make up white light. And then you have infrared, which is in simplified terms the heat signature that we can detect from objects. And then you have microwaves, and then you have radio waves. Microwaves, the more energetic part of radio waves. Now, in understanding these, we are able to then have things like your satellite radio, cell phones, radio broadcasts, where a person is sitting in studio with a microphone, they'll cause vibrations, sound comes out, captured by a microphone, electrical signal is carried through to some other equipment that convert whatever message into radio waves, and it is broadcast in all directions. It's cheaply transported. You don't need cables from the broadcasting station to homes of different people. It's thrown out into the air. If you are within a reasonable proximity, you need only an FM receiver. You tune into that frequency and you are able to listen to the station. So they're all around us. Microwaves. We would not have the ovens that we use at home. People call them microwaves. No, they're not. They're ovens which use microwaves. So it's a microwave oven. Okay? Microwaves are a radiation type. Now, microwaves, you'll find that because we understand how they operate in nature, we've been able to now build a contraption where you have them. You switch it on, you put your food in there, and you have them interacting with your food. Interacting with your food to the point that molecules start to vibrate. As they vibrate, those molecules cause heat, and that heat will cause steam, and your food gets warmed up and or cooked. Very simplified way of explaining it. That would not exist if we did not understand how it operates in nature. We get to infrared. Infrared, before Bluetooth technology to send contacts and media, pictures and all these other things. Infrared was relied upon for basic things such as exchange of contacts. Phones like back in the day, Nokia 6310i. I'm not certain about the 6210, but those phones used infrared. It was before we had Bluetooth. Now, that's just an aside, just a little bit of an example where I remember us using it for that. Nowadays, you also have infrared thermometers. You no longer take a thermometer and hide it in warm places to get temperatures of babies or toddlers or whoever else. You point something at a person, it gets a signature, it gives you a reading, digital reading. It's called IR thermometer, infrared thermometer. TV remotes, a lot of them relied on infrared. Night vision equipment by soldiers and all of these use infrared so that they are able to, at night when they cannot see, be able to get a heat signature from an object. They see when something does not have a lot of heat that it's emitting, or when it's animals, they can see it's a four-legged animal. It's definitely not a human being. Oh, we see this is a two-legged organism. Those type of things, those are uses, practical uses that these are used for because there's an understanding of how they operate in nature. Moving right along, we get to optical, as I said. Well, optical is what we rely on to be able to see one another. Moving right along, we go to ultraviolet, just to show you the ones that you might not be too familiar with, because optical, a lot is usually dealt with regard to white light and it going through a prism and dispersing into the 7 colors that make it up. We talk of refraction, the bending of light as it moves from one medium to another. We talk of reflection, where it gets to a surface and then it bounces off, moving in a different direction, and you'll talk of your angles of incidence and your angles of reflection and all of that. Now, ultraviolet, people will tell you of the dangers. You could get skin cancer and all of that. But practical uses of this, you may have been to shops where they take your money and put it under a certain type of light. That's for them to determine that your money is not counterfeit, it's not fake, it doesn't have funny dyes that are part of the paper. Detergents will tell you makes whites whiter and colors brighter and all of these things. You find that in the detergent there are substances that get reflected, that reflect light, pardon me, that reflect UV once they are outside. So you wash these things and those substances stay in your clothing when you are outside and you have this UV hitting your clothes. A lot of that is reflected such that your clothes seem more lively, brighter, cleaner, and all of these things. Moving to x-rays, let's say I was playing soccer. Somebody dribbles me, I take a wrong turn, I try to backtrack, something happens to my ankle. I get taken to the emergency room, get taken through for an x-ray. And they look at that area. And in the way which they try to find out if I have a broken bone or a crack is that they have this machine giving off x-rays. X-rays will go through the soft tissue, go through the skin, go through inner material, but when they get to the bone, which is dense and having your sodium, your calcium and all these things, the x-rays will not penetrate, and all you'll have is an image of the skeletal system. Basically, it will show you on that image, that radiograph, that all the gray areas are where the light simply moved through, the x-rays moved through that, but where you have this white image is where it got absorbed. So if it was my chest area, you'd have all of the ribs showing, and then in between you'd have all of the soft tissue, it would be grayish. But where you're supposed to have a bone and there's a black grayish area, it means that the rays have passed through that area, which then means there is a missing bone, and that is where they need to give attention. It's broken, it's cracked, and all of that. So if it was my hand, it should be this white image of my hand, but if there's an area which might be black on the image, it means that the x-rays moved through there where they shouldn't have if there was bone. Now moving to gamma rays, the most dangerous, the most energetic, and that's why when we talk of nuclear material, radioactive material, we are mentioning it emitting gamma rays. UV, X-ray, and gamma rays are very dangerous. They might cause cancer. Gamma rays might even kill a person, organ failure, and all of these things, depending on exposure. But because we understand how they operate in nature, we are able to use them for good. I've said a bit about X-rays. I've said a bit about ultraviolet. But coming to gamma rays, we find people that have cancer, you have radiation therapy applications, where person is given medication goes to the areas where there are cancerous cells, and then radioactive isotopes and other substances and other material that has been worked on in labs is used, and it is bombarded. They shoot at those cancer cells, those regions that have these markers on them, and they're perhaps able then to give the person a new opportunity to live a healthy life. So it's important that these things are studied, they are understood. No one person will understand all of them in depth, but it is very useful that as society, as a people, we understand that science is everything that is around us. Even the daily things and encounters that we have are scientific, and we need to be open to the sciences and encourage young people to take up the sciences. Not to say that anything else in terms of fields that we might talk of or careers are less important, but we are talking to this fundamental understanding and openness to the sciences that is very important. And with that, I'll leave it. In future, perhaps I'll have shorter installments, but I wanted to just try and incorporate everything, no particular order of significance, but just as it comes to the mind and just as how one may lead to one another. All right, with that, I thank you, and be sure to tune in for any future installments I might have. Thank you.